Hello and welcome to a video where you will learn about polar coordinates. Polar coordinates. So, what are polar coordinates? Well, they're very interesting coordinates. I can tell you that. Now, we used to our normal coordinates, the x and y. You've probably known this all your life. And this system of coordinates is called the rectangular coordinates. So, I have my y and x axis, and any point P is denoted by an x coordinate and a y coordinate. And drawing dashed lines, you'll see that rectangular aspect of it, right? It looks like a rectangle. You go right some units, x units, and up y units. And so what if there's a different way where we could denote point P? Well, there is. That's polar coordinates. Okay, so we want to make our transition from the xy world all the way to the polar world, where it's denoted by r and theta. So how is this different? Well, we first need to define our pole or origin. See here, we had an origin which was 0, 0, the well-known origin. Now we have a pole. And from the pole, we'll have a polar axis extending to the right. And that's it. You don't need a y-axis, you don't need an x-axis. All you need is the pole and the polar axis. And so how would we graph r and theta? Well, say r theta is P, point P, like we had here. Now over here in the rectangular coordinates, we had point P, which had the property of being x units away horizontally and y units away vertically. We could also see that the distance from the origin or the pole to the point has some length, and we'll call that length r, or the absolute value of r. If r is negative, we want it to be positive. And the second defining property is the angle made with the polar axis theta. And so here we had x and y, two pieces of information that were enough to define a point, but we also have a length and an angle just as sufficient to define a point P. And so we're able to write it as r theta. And now you just have to be careful. You can't take this r theta to the rectangular coordinates and say this is r and this is theta. No, these are not the same points. This is like P prime. This is a system and this is another. So now I want to give you some examples. Let's say I want to graph 1 pi over 4. Well, we'll take a length of 1, extend it to some point, P, and our angle here will be pi over 4. Oftentimes, it will be helpful to have these axes, because if you're used to the unit circle, you're used to the angles here being pi over 2, pi, 3 pi over 2, and, well, 0/2 pi. And so the axes are not necessary, but they're helpful for your angles. Okay, let's take another example. Say we have 3 negative pi over 4. Okay, well, what does the negative mean? Well, a positive angle denotes a rotation counterclockwise. When we have negative, we go clockwise. So we'll have this point P with pi over 4 and length 3. Okay, let's take another example. Say I have 3 pi over 4. That'll be somewhere over here. Length 2 and 3 pi over 4. Now that we've seen some examples, I want to talk about some interesting properties. Let's draw our pole and polar axis again. Say I have some point P again, denoted by r theta. What happens if I take my theta and add an angle of 2 pi? Well, 2 pi is 360 degrees, meaning I could rotate and I'll end up in the same position. This is 2 pi, a 2 pi rotation, meaning our point is equivalent to r theta plus 2 pi. But we could rotate again and get r theta plus 4 pi. Or I could go the other way around, minus 2 pi. For example, I'll have r theta minus 2 pi. Well, what we have here is periodicity, something you see in sine, cosine, and tan. We're adding some quantity of pi, will take you to the same position. And so we can write down that r theta is equal to r theta plus 2 pi k. K here is any integer. It could be positive, negative, that's what an integer is. So it could be 2 pi, negative 2 pi, negative 2 pi times 300, it doesn't matter. We're still rotating and ending up in the same place. So let's write this down here. Okay, we have more interesting properties. So this is the first one. Our second is, take a point P again, with r theta, and go ahead and multiply r by negative 1, or switch the sign. What essentially happens is that you reflect it across the pole. It will end up right here. It'll be negative r theta. Now, this should be a straight line, but I draw poorly, so it doesn't matter. But we do have another way of representing negative r theta. You see, we take the angle difference between these, and we know that on any line that we have 180 degrees. And so this is pi radians. And so negative r theta is equivalent to r theta plus pi. So our point P could end up in the position P prime if I multiply r by negative 1, reflecting it across the pole, or I rotate the whole point pi degrees, oh, not pi degrees, pi radians, which is 180 degrees. And remember here how we had basically infinite representations of the same point? Well, we could do the same thing here. We could add a 2 pi and we'd end up in the same place. So this is equal to r theta plus pi plus 2 pi, the 360 degree rotation. You'll end up with 3 pi. Add another 2 pi, you'll end up with 5 pi. And if you notice here, you have 1 times pi, 3 times pi, 5 times pi. So it's all the odd multiples of pi. So writing this down in its most general form, negative r theta is equal to r theta plus the odd multiples represented by 2m plus 1 times theta. Plug in any integer n and you'll see that 2m plus 1 is odd. Okay, now I want to cover something that's very important and very interesting. This is something you see quite a lot in math, where you have two different things and you want to build a connection between them. You want to build a bridge. And so we just learned about polar coordinates. We know about our regular rectangular ones. We can connect them. How? Well, let's draw some axes. And we'll see that our point P, an arbitrary point, can be represented by x and y, the rectangular coordinates, and also by r and theta, r theta. And so here, if you give it your attention, you'll see that this looks like a triangle. And in fact, this is the key. You can draw a line. We have this segment and this segment forming our triangle. We know that the length of this is y, because this is point P, and this has a distance of x. I'm just going to write the x over here. Very nice. And using very famous properties of triangles, we can find out the connection. So we could take, for example, the sine of theta. The sine of our angle theta will give us opposite over hypotenuse, which is y over r. And the cosine of theta, adjacent over hypotenuse, which is x over r. You can rewrite both of them, solving for y and x respectively. We'll have here y is r multiplied by sine theta, and x is equal to r cosine theta. And look at that. We can go from our polar coordinates to our rectangular using this. If I have my r and if I have my theta, I can get my x, and same goes for y. Now, we have established a very important connection between our rectangular coordinates, our angle theta, and r, the length. Well, the length here is the absolute value of r, if you remember. I said r could have a positive or negative sign, should be kept, you shouldn't remove it. Well, if r is negative, keep it negative. that will deal with x and y and their respective signs. And so, could we find a connection with only the rectangular coordinates and r? Well, yeah, we could. We could use the Pythagorean theorem. That's just x squared plus y squared equals r squared. And this is one other connection we should keep here. And for the final bridge, we could make a connection between the angle and the sides. So that would be tangent theta is equal to opposite over adjacent, which is y over x. And so we have a connection between rectangular coordinates and r and theta, rectangular coordinates just r, and rectangular coordinates with just theta. And these equations can be used to go from Okay, now that we've learned of this connection, let's try an example and see if we can apply it. Say we have the rectangular coordinate 2, -2. And I want to change it into the polar coordinates. So let's just say polar. So we need to figure out two things, r and theta. So let's begin by drawing some axes, the y and the x-axis, and plotting the point. That would be 2, -2, just over here. Let's go ahead and draw a line where the length is r, or the absolute value of r, with an angle theta. And so we need to figure out the angle and the length. Using this formula right here, the Pythagorean formula, we can get the value of r. That would be x squared plus y squared equal r squared. X is 2 and y is -2. So that would be 2 squared plus -2 squared is, well, r squared. This means that 2 squared, which is 4, plus 4, that's 8, is r squared. Taking the root of both sides, you'll see that r is positive -2 root 2. I'm just going to take the positive. Okay, why did I choose the positive one, not the negative one? You can choose either and work with either. As long as the combination of r and theta gives you the point, all will be fine. But let's work with the positive one. So r is 2 root 2. And for the angle, I'm going to use this identity. Tan theta is equal to this theta, -2 over 2. Since y is -2 and x is 2. And this is equal to -1. Taking arctan on both sides, you'll find that theta is -pi over 4. So putting it together, we'll find that our point is 2 root 2 -pi over 4. Now let's verify, is this correct? 2 -2 in polar coordinates is 2 root 2 -pi over 4. And this checks out. We see that if we go -pi over 4, which is pi over 4 but clockwise, we'll end up in the fourth quadrant, which is correct. Now, do we have other representations of our coordinate? Yes. Remember, we have these two equations that give us equivalent representations. For example, I could take my point, 2 root 2, and I could add a multiple of 2 pi to my angle. So that would be pi over 4 plus 2 pi, or -pi over 4 plus 2 pi. And this way you would have 7 pi over 4. So 2 root 2, 7 pi over 4. That's one representation. We could also use this one here. I just realized this. Okay, I just realized this should have been pi. It's fine. This is pi. There you go. And so essentially what this second equation tells us, we have two equivalent points. If you change the sign of r and add an odd multiple of pi to the angle. And we can do that with our polar coordinates here. So that will be -2 root 2, -pi over 4 plus some odd multiple, say 3 pi. So that would be 3 pi minus pi over 4. I think that's 11 pi over 4. And that's it. We have three equivalent answers, and we also have infinitely many, since we could keep applying these equations to get more representations of the same exact point. So when you're asked to go from rectangular to polar, you'll have multiple answers. But don't worry, all of them are correct. Okay, so now I want to go from polar coordinates all the way to rectangular coordinates. So I have 4, 2 pi over 3. 4 here is the r, and 2 pi over 3 is the theta. So how does this look like? We'll draw some axes to help us out. And we know that 2 pi over 3 is just pi minus pi over 3. So that would be here. This would be our pi. And this would be pi over 3. All in all, this would be 2 pi over 3. And our length is 4. Okay, well, we could use our equations over here. And we'd see that y is equal to 4 times the sine of 2 pi over 3, and x is 4 times the cosine of 2 pi over 3. And this will give us negative 2 to root 3. This tracks. We have negative 2, which would be here, and 2 root 3. If you notice, going from polar to rectangular, we have only one representation, and that would be negative 2 to root 3, as opposed to the many representations we could have in polar coordinates. And so I think it's very important to highlight this point, where we have our polar and we have our rectangular. We start out with something like r theta, and here like x, y. And say we're asked to go from polar to rectangular, and well, we can do that. If we go from rectangular to polar, we can also do that in multiple ways. So I can either go like this, we go from xy to r theta, or I go from xy to r theta plus 2 pi. Remember, these are equivalent, so both answers would be correct. I could also go to negative r theta plus 2n plus 1 pi, and this comes from our second equation over here. And so going from rectangular to polar, I end up with multiple answers which are essentially equivalent. Going from polar to rectangular, well, I end up with one answer, and I could choose to start from any of these, and I'd end up in the same place. Now for a very interesting exercise, I'm going to take a famous graph or equation, and that would be y is equal to x squared over 4. And so I want to take this equation of a parabola and turn it into a polar equation using, well, polar coordinates. Let's first rearrange so it looks nicer. We'll multiply by 4 on both sides. 4y is x squared. And I'm just going to use these individual equations. So y is r times sine theta, and x is r cosine theta. You get r squared times cosine square theta. We can divide by r times cosine square on both sides. This will simplify things greatly. And we'll get some nice cancellation. We'll have 4 times sine times 1 over cosine squared is equal to, well, one of the r's cancel, and we're left with r is equal to 4 sine 1 over cosine. It could be rewritten in this way. R is equal to 4 times sine theta times, well, 1 over cosine is secant, so that's secant square theta. And this is a polar equation of a parabola. These are equivalent. And so how do the graphs of the polar equations behave? Well, we'll see that in later videos. And now last but not least, we're going from polar equations to, let's say, rectangular equations. Say I have r is equal to 2 plus 2 cosine theta. And this is polar. I want to take it to the xy world. So you can do this in multiple ways, but I'll first multiply everything by r, which will help me. Here on the left side, we get r squared is equal to 2r plus 2r cosine. How did that help? Well, now we have r cosine, which is x, and we have r squared, which is x squared plus y squared. And so that greatly helped. So that's x squared plus y squared is equal to 2r plus 2x. Let's isolate the 2r, and we get x squared plus y squared minus 2x. And so now it will be great if I have r squared instead of r, so I can just use this. So we can square both sides. We'll get 4r squared is equal to x squared plus y squared minus 2x all squared. And we can replace the r squared now. It will be 4 times x squared plus y squared is equal to x squared y squared plus 2x all squared. And this is how we've gone from polar to rectangular. And as you can see, the equation is much simpler as a polar equation. So we find out that some graphs are more naturally written in polar equations than in rectangular. I mean, look, this is a monstrosity. You don't want to work with this. But this is nice. And now that's it. We're done. I'll leave you with the graph of this equation. It's a cardioid, and it looks something like this. Well, I've exaggerated it, but it's called the cardioid because it looks like a heart. I think this is how you write it. I doubt it. Maybe. I think it's correct. Anyways, and that was it. And that's all. I hope you learned something. I was gonna fall. I hope you learned something. I hope you enjoyed. I'll see you in the next video.